Hello all. My name is Kipras. I'm from OCI, Oracle Cloud Infrastructure. And today I'm going to talk about reloading Nginx or changing configuration of Nginx without actually reloading. So what that actually means in general is that it's about partial configuration update. So when you have a proxy server with many configurations for different hosts, it's about changing one of the hosts without actually restarting the server. It's actually harder to do than it sounds. So a bit of an overview. So I'm going to talk a little bit about Nginx, just a quick intro. Then I'm going to talk about how the configurations are updated normally. Then how there are the existing solutions which work in some cases. So what you can do, how you can do it yourself. And then actually implementing full partial config updates. And why is that difficult? Okay. So just kind of quickly, these people here. So how many of you know what Nginx is? Just a quick show of hands. Anybody use Nginx? And maybe someone actually modified the Nginx source code? Custom builds? No? Okay. So just really quickly, so Nginx web server, very fast and event-based, so that's why it scales very well. These are old metrics comparing it to like kind of old school server like Apache. Basically, the performance benefit is because Nginx is event-based, it doesn't create new threads for every single request or connection, so it doesn't use as much memory. That's kind of the gist of it. Very sample configuration. So this is a very sample, just a proxy from some client to a server, right? Kind of simplest as it can be. So basically, this configures a load balancer over those two IPs there at the top, and that's it, right? Nginx has a couple of processing models that differ by a little bit. You can use single process, or you can have multi-process. And generally, you do single process if you're debugging something, and then multi-process if you're in the actual production. And the multi-process nature of it affects the hot reload portion a lot. So, and I'm going to get into that a bit later, right? And generally, you configure as many workers as you want to allocate CPU cores for Nginx, right? Because one worker can only use one CPU core, as it's one process, right? So multi-process, what is it and how does it work? So when Nginx starts up, when it reloads, it reads all the configs from the disk or wherever. Then the master process, it reads all the configuration, it starts up. Once it read all the configuration, validated it, and said, okay, all configs are good, I can run, it uses the fork call to create the workers, right? So the workers are essentially the same process, but now they are able to actually proxy the traffic, right? So that's kind of the gist of it. One clever trick that happens here is that each worker gets its own virtual copy of the config. So what that means is that the config data that it read, it resides in each of the workers, but it's the same. And also, it's a virtual copy in the sense that it's not actually copied in memory. So what happens is the memory consumption does not increase with every worker. It increases a little bit, but it doesn't fully increase because of that copy on write mechanism, right? So you get it memory-wise, it scales really well that way, right? Updating configuration. So let's say I wanted to add that last line there, proxy timeout 5 seconds, right? So you change the config, then you send a hang-up signal to the master process. And what happens is, so these are the processes. We send the hang-up signal to the master PID. And now you see the two old workers that are shutting down, and then there's new worker processes starting up, right? So that's kind of the gist of it, right? And all is well if you don't have that many configurations. Reloads are cheap. They happen pretty fast. But if you have lots and lots of configurations, this becomes tricky because, well, let's get into why it becomes tricky. So let's say you changed only one configuration. Reload rereads all of those configurations. So it takes time to read and process them. DNS addresses have to be resolved. So if your upstreams are actually domain-based, not static IPs, but they're domain-based, they have to be resolved. And the resolution actually takes a lot of time if you have, for example, upstreams which are, let's say, S3 buckets, right? So in that case, the TTLs are pretty low, like 60 seconds. So they'll time out pretty fast. You can't really cache them, or cache is not really effective, right? So that's the first problem, that it takes a long time to reload. So if you have one simple change, you expect it to, apply fast, but it doesn't really apply fast, because the more configurations you have, the slower the whole reload process happens. Then there's another problem. When you do a reload, both old workers and new workers run at the same time, so your memory consumption is effectively doubled. So you get this kind of a heartbeat pattern for your memory usage, right? So each of these jumps up is a reload, right? And if they take a lot of time, then it might actually be even worse, because those jumps may, happen for an extended period of time. Right, so you may end up with something like this, where you have workers from one reload, then workers from another reload, then workers from another reload, and all bunch of workers now taking up a lot of memory if you have a lot of configurations. And so, well, another problem is that a worker doesn't really shut down until the connections that it was serving have been closed. So in other words, if you have connections that are running requests through a worker, what happens when it's shutting down, it gets the signal from master saying, hey, please finish all your work, please finish all the requests, and then shut down, right? Which is okay for normal requests, but you have things like WebSockets. WebSockets, you can't really close that well, because it's a transparent protocol, right? You can't go inside and say, well, please shut down now. So it becomes more tricky. You have to do certain tricks, or you have to, in essence, forcefully shut down the connection at some point, which may be problematic for some clients, right? So this creates a lot of problems. So if you have, like, for example, in this example, there's workers from 4 different generations. So now it's 4 times the memory usage, right? Because each generation means separate configs. Those separate configs have a separate copy. That can add up pretty fast, right? Yeah, so I kind of talked about this already. So we're all familiar with this. When this happens, it's bad when this happens in your production server, like not this window, of course. Then it's even worse when this guy comes around. So if it's really out of memory, then Linux kernel will just start shutting down processes at random. This is the worst thing that can happen to your service. But so what's happening is, essentially, instead of, when we need to change a tire, instead of changing the tire, we're kind of reassembling the whole car, right? Because if we want to change one simple thing, we're rebuilding all the configurations. So that doesn't really make a lot of sense. So why does it work that way? Well, first, because it's simple. When you think about any kind of service, any kind of program, there's not really a lot of examples of software that would allow you to change the configuration without actually restarting the process, right? Because it creates all kinds of complications. And generally, for the most part, you generally don't really need this, right? So, and also, so it's much simpler to build it with a simple reload, right? You just kind of shut down the process, start up the process, that's it, right? So, it works, but it only it works for most cases. So like for the case where you have a lot of configurations, you have the problems that I just mentioned, right? So, well, when you sit around and you think, well, there has to be a better way, that there has to be a way to kind of fix this, to improve, right? So let's see what can we do, like how can we fix the problem? So the first thing that you can think to do is to actually have separate instances for each of those configurations, like each virtual host, run a separate Nginx, right? Done. That's it. So it's more, so depending on how you set up Nginx, and because you have many virtual hosts, then it's probably some kind of automated system. You have building a proxy that's configured with a UI for many clients, something. So that affects how you set up the actual running of Nginx, because that means it has to listen on separate ports, each of those instances. So it's more headache that way. But if you can set it up that way and it works, then that's it, problem solved. For one client, the changes will apply pretty fast, because that's just a reload for that single Nginx instance, right? The problem, though, there is you'll have more memory usage because each Nginx, that means separate binary in the memory, and then anything that you would share otherwise. Like in some cases, that's just not a viable option, right? But yeah, it would fix the config changes, propagation time, but would severely increase the memory usage. And also, it doesn't fix the problem of workers staying in shutting down state. If for that specific client, for that Nginx instance, there's workers that are still proxying that WebSocket traffic, well, you still have to do something about that problem. Another option is going commercial with the commercial version of Nginx Plus. So Nginx Plus has this module called API module, and it provides a RESTful API endpoints for updating certain things. So for example, you can manage the upstream servers. So you can actually add and delete them without restarting the server or reloading the server. There's also all kinds of status information and other stuff, and you can check it out at that link. But of course, Nginx Plus is a paid service, and depending on your company or your project, we might just not be able to pay for it, or you might consider that it's not an option for you, but it is one of the options, right? Another option is T-Engine, and T-Engine is a fork of Nginx, which is a bundle. So it takes Nginx, it takes some third-party modules, bundles them all together, and ships them as one thing. One of those modules that it bundles, it's called DIUPS, which stands for Dynamic Upstream. And it works in a similar way that the Nginx Plus module works. So it allows you to update the upstream list. Also with a RESTful interface, it's a different interface, but the gist is the same. You can change the upstreams without reloading or restarting Nginx. But to do that, you have to use T-Engine, right? The bundle of T-Engine. Or you can try to take that module, integrate it into Nginx. Right? And also there's OpenResty. OpenResty is another bundle of Nginx, like T-Engine, but a separate project. And let's look at a couple of projects that are built on top of OpenResty. One thing that's special to OpenResty is one of the modules it bundles is Nginx Lua, which allows you to script the internals of Nginx with Lua. So if you need more customizations than the actual Nginx modules allow you to do, that's a pretty fast and rather simple way to get it done. You don't have to write C modules then. And there's projects that utilize that capability. So one of those projects is Kong. And Kong is an open source API gateway that runs on top of OpenResty. It's open source. You can go to GitHub, download it now. And it has an admin API. And that admin API provides endpoints for, same thing again, upstream servers management, managing API routes. So it's an API gateway. So you have routes like, for example, when there's some URL incoming, you want to route it to some server, or some other URL, you want to route it to a different server, things like that, right? You can manage SSL certificates on the fly. You can manage plugins. So Kong has a pluggable architecture and other things. So all these things happen for the admin interface. Everything you do, all these things happen without reloading OpenResty in this case. So that might be an option, right? Another project is Redix, which Nginx on, I think it stands for Nginx on Redis, or Redis with Nginx, something like that. It's kind of a similar thing. It's a plugin that allows to do dynamic Nginx configuration, but it's unfortunately the project looks dead. I think the last commits were like 2017 or something. And last but not least, you can always build your own management. If you need something then updated on the fly, you can build it in Lua if you use OpenResty, or you can build C modifications, modules with C. And a lot of people do that when they, really need this. And the last option, which we're going to discuss in depth, is actually going kind of all in and implementing full support for changing Nginx configuration on the fly. Now, what that means is you basically say, hey, Nginx, take this config and use it now without restarting. So instead of starting it up and reading from the file system, you have the same Nginx instance and say to it, instead of the previous version of that vhost, now use this one. And we expect everything to just magically work, right? So why do we want to do this? Well, in our case, only modifying upstreams is not enough. We need to be able to change a lot of other settings, not just the upstreams. And as you saw from the previous options, most of them were about changing the upstream list. But if you use a lot of directives, then that might not be enough. So if you use a lot of directives and now you have to kind of re-implement them in some other way so that you would be able to do the changes on the fly, well, now you have a lot of configuration that you have to retest, deploy, face possible bugs and all that kind of stuff. So why do that? And also, we want to make sure that everything works the same way. So we kind of said that we're going to bite the bullets, implement this in Nginx, and if we implement it right, then any changes that we make should work the same way. It doesn't matter if they were from the startup of Nginx or if they were deployed with these dynamic changes, right? That's the idea. So, well, shouldn't be too difficult, right? So let's talk about the battle scars then. So some of the decisions and challenges that we faced along the way. So the first question is, well, how do you even start the update? So there's multiple ways you might want to do this. You could use Unix signals like Nginx does there, like with use signal user or some other signals. That's one way. You can use Unix sockets. So Nginx can listen on a socket. So you can send all the configs through a socket server. Have some kind of agent that runs in your machine and then supplies the changes, listens for the response from Nginx. Because one of the things that is wrong with signals, or maybe not wrong, but it kind of complicates things, is that a signal is a one-way operation. So you basically say to Nginx, hey, reload, but you don't get anything back. So you don't know if it succeeded, if it failed, or if it succeeded when it succeeded. So with a socket, you can actually, you can have a conversation. You can make a request saying, update the config, and you can actually expect it to return something back. You can also listen on a message queue, right? You can send changes with a message queue if that works. But then Nginx is a web server, right? So it only makes sense to have the updates running as a, HTTP server. Okay? So how do you actually do the update? So it turns out that you, in essence, just run the same code that Nginx runs when it starts up, when it reads the configs. You can run the same code, and kind of for the most part, it works. There's a lot of quirks that I'll get to, but for the most part, it actually just works. Maybe I shouldn't have said just works, but it works sometimes. So this is just kind of one part of Nginx source, which initializes the HTTP, well, part of the HTTP module's initialization. And this is one of the parts that you run, and those things actually work. So in a single process model, that will work. Are there any complications when we do the multi-process model? So let's kind of rewind a little bit. So we talked about this system where Nginx starts up, reads the configs, and then it forks itself. And the workers are actually forks of the master. Okay? So let's say here we have our 4 workers, and then there's a config update request coming in, right? And one of the workers catches it. So what happens? It catches it, it updates the config, but the config stays in that single worker, right? Because again, it's a virtual copy of the configs, but it's still a copy. So now it's only there, right? But requests come in through all of them. So that's not good, because now you'll have requests coming in, and 1/4 of them will be with the new configs, and the rest of them will be with the old configs. That's not good. But thankfully, Nginx has a shared memory mechanism. And that is used already by a lot of modules. So the problem with the fact that there are separate workers that are separate processes, it affects other parts of Nginx as well. So they came up with a way to use shared memory to share that data, because a lot of things wouldn't be possible without it. So some examples that what uses it is the proxy cache, the cache for caching responses on disk. SSL session caching. So if you have connections and you want to share you want to cache the SSL session, so they wouldn't have to be reinitialized depending on how many workers you have. You can cache that. There's request rate limiting, which rate limits requests. You basically say that I want to drop all requests that exceed 10 requests per second or something. But those calculations have to be done in the entire server. If you do it in one worker, then they break because they depend on how many workers you have. So things like that have to be shared. Okay. What just happened? And various third-party modules also use that. So we can use this mechanism to create a new type of memory pool, which is a shared memory pool, and put those configurations there, right? And so with that, we get this, right? A worker catches the config updates, and now the config update is in all of the processes because we changed it in that process that caught the request, but because all those configs are now in shared memory, in that shared memory block, it automatically is updated in the other workers, right? You didn't have to do anything. So that's good. That solves that. But then there's a complication that arises from there. So again, those workers, they had a copy of the configs initially, right? But now it's not really a copy. Now it's shared. Now everything you write in one worker ends up in the other worker as well, right? Which helps with the config propagation. But there are some quite nasty situations that can happen if you're making changes in a memory space and another process has the same memory space, but it doesn't expect changes to be made there, right? So if you have code that expects that the data that I write is only accessible to me and cannot be written by another process, that can lead to problems, right? And that's all of Nginx code, right? Nginx is built with that idea in mind that it doesn't matter if it's one worker, two workers, three workers. Everything I write, it's for my process. So you can change configs on the fly now. That's good. But what about old configs? What about the previous version, that version 1? So you can't just delete them because, again, there might still be connections and requests that are running, right? But we can't keep them around forever, because if we keep them around forever, that'll just leak memory. So that process just becomes a big memory leak. It'll just over time will just consume all your server memory. That's not good either. So you reference count. You keep a counter of how many connections use a specific config. After the updates, once the config reaches 0, the counter reaches 0, you can now safely discard that config. Right? That's quite simple. But that means that now you need to track all the allocations that belong to a single vhost. So that virtual host has to be kind of a container for all the things that are there, right? You have to track it so that you could free it. So for that, again, memory pools come in handy. So Nginx has memory pools where essentially you say, I want to allocate something. I have a pool and I want to allocate something from there. And you don't have free. You don't need to free the specific thing. You free the whole pool once it's done. And it uses that for connections. It uses that for requests. For example, when a request happens, all the allocations happen in that pool. And then once the request is over, that pool is just freed. So you don't have to track memory usage. So it's a very neat and nice idea. So in this case, every virtual host, the config that we want to update gets a container. Container has a reference counter, memory pool, reference counter reaches 0, memory pool can be freed, right? So is that it? Well, no, that's just kind of the first part. There's way more tricky things. So one of the things that can go wrong is what happens if you have a standard reload and that partial reload at the same time, because you will still need to reload, right? Most likely from time to time, some change will happen that will cause you to reload. And there's different ways you can handle this. So one is when you run a full reload, for that time being, you disable partial reloads. So the partial reloads will return an error, something, timeout, something. So the good part is that that's simple, right? It's quite simple to do. The problem is that means your partial updates will be working, not working, working, not working. And when they're not working for an extended period of time. So that's a problem. Another option is locking the config of that single vhost. So when you do a full reload, you basically essentially change configs one by one. And then only if it happens that while the reload is changing that one config, also partial update comes in to change that one config, well, it'll only have to wait for that one part, right? So for the most part, both full reloads and partial reloads should work without interruptions. Right? The problem is that this is way more complicated, and also you can have race conditions with this. And one other option is basically when you do a full reload, you just basically have a new fresh. You start up with fresh memory. So that shared zone, just create a new one, basically. So then those two things, the full and partial reloads, they don't interfere with one another, because the partial updates will still happen in the old memory. Right? So that's simpler, but that still has race conditions. Because so what happens is, so let's say you have a full reload and then a partial reload comes in. So now you don't know which part are you updating, at least in that middle option. Because it might happen that after the full reload, you might have the version that came in with the partial one or with the full one. It depends on the time, when it all happened in time, which happened first. So that's tricky as well. So in the end, it just depends on how your system works and how you want to do this, the full behavior of your system. There's more variables that come into this. So some Nginx modules actually mix per worker data in their config structures. So that's a really bad thing. For example, upstream connection keep alive, the module that allows you to have keep alives to the origin, so that you wouldn't have to do another connection every single time when you're proxying, right? It's a thing you really should use. It improves performance, reduces latency. But it keeps connection keep alive right there with the config. So now, when you update the config, when one worker stores a keep alive, it actually affects the other workers as well. But workers have connections separately, so you can't really share that. Bad things happen if you share it. So in that case, you kind of just take these things which are per worker and you separate them out. You separate them into different structures that are per worker. There's another thing called a temporary pool. So when Nginx loads up the configs, there's some temporary data that's only used while parsing, doing certain things, and then it's discarded because it's no longer needed. But for the partial updates, there might still be things there that you will need to actually have that partial update work, because it's the same config processing. So that's actually quite simple to solve. You just take that partial data, and you move it to a permanent pool. Instead of a temporary pool, it's now permanent. It just stays there. Then there's file descriptor issues. So what's that? So a process can only open the same file one time, or more technically, it can only really have the same file descriptor can only be there once. You can't have two file descriptors, because then the conflicts happen. If you write to one, you write to another one, the pointers mess up, and there's bad things that happen. So you can fix that having a file descriptor cache. So essentially, you say that if I'm trying to open a file, but I already opened this file in this process, then I'll just return the already opened file from that cache, right? And that fixes that. But then there's a problem. What if you open a new file? What if you deploy a new config? It opens a new file, a new log file, for example. So this is kind of a description of how the fork works. Why when Nginx forks, that's not a problem, because the fork actually duplicates the descriptor. So each worker gets its own kind of, I don't want to call it a copy, but it's kind of a copy. So it's the same descriptor, it's the same file, but they all can write to it, and it works just fine. There's no problem. But so for new files, you have to do this yourself. You essentially have to, one worker will open that new file, and then the others have to take that descriptor, and you have to duplicate it for it to work there as well. You essentially have to mimic the behavior of fork for this to work. And then for Lua code, so if you use OpenResty, again, one of the great things about it is you can script a lot of things with Lua, which is very simple, very fast. If you run LuaJIT, which you really should, each worker runs its own instance of Lua VM. and each Lua VM has its own cache of embedded Lua code there. That's done for performance, right? Lua JIT compiles the code, it stays there. You don't need to change it. So, or if it doesn't change, then just cache it. Runs much faster that way. But so if you update if the config changes that you pushed have changes to the Lua code, then the problem is that it doesn't get picked up because the cache key is actually the file name plus the line number. So it essentially just says, well, when I want to run some Lua code, where is it? Oh, it was for web app something, and then line 12. That didn't change. It's still the same position, so I'll just use it from the cache. Right? You have to invalidate the cache in all of the workers. So to do that, essentially you just add a hash of the code itself and put that into the cache key. So that way the hash changes, and new workers, they pick it up, they recompile it. So I think that should be enough of problems. There are other issues. This is actually not all of it. That you kind of have to iron out if you go this way. But it is possible to make it work. So, and with that, time for any questions, if there are any. Everyone's saying like, yes, I'm going to go home and do this right now. This is clear. Okay, then I won't hold you up anymore. This is the end of the conference. So thank you and have a nice rest of the conference. Okay.